I'm not homotopy theorist, but recently started to realize that I should be. Uh, Okay, so a lot of this is joint work with various people. And I entitled the talk Derived Analytic Geometry. And so this is we kind of like followed work of Tohen Betsotsi and Lurie on derived algebraic geometry. And derived algebraic geometry is like framework for including derived intersections and Tor groups into some structure, sort of generalizing algebras. So for instance, simplicial commutative rings. And in fact, geometry in general, you can think of as sort of commutative algebra plus growth-induced topologies. So we were sort of trying to understand whether analytic geometry could be phrased in a similar way to algebraic geometry. And maybe there's kind of general geometry that you just do everything at once, and then you sort of input your symmetric middle category, and you get either algebraic geometry or complex analytic geometry or dyadic geometry, which was mentioned in the last talk. So I'm going to be talking about, let me start my talk with a more recent framework due to arXiv, following some work of Brandner and Matthew, which I'm going to mention. So, homotopy theorists are very used to dealing with stable, presentable, symmetric normal categories. Okay, so we have tensor product and unit and this kind of internal mapping object, which I'll just denote like this. So you can think of mod Z as the sort of silliest example of this, which I'm going to be talking about. But this this by itself is maybe a way of doing an analog of topology or spectra. I don't think you can necessarily push this so much towards geometry without an extra structure, which is a T structure. So what you ask for is and a compatible T structure. Oh, sorry, and a T structure, and I'll say what compatibility means. So that's one. The negative part is closed under filtered code limits. Two, the unit is in the positive part, which, I mean, that's familiar from spectra, right? And the positive part is also inherits this symmetric normal category. So if X and Y are in C bigger than or equal to 0, then X stands for Y. And so this T structure allows me to define new concepts that I don't think you can make sense of without the T structure. So let me say what those concepts are, and those are crucial for geometry the way I see it, as opposed to just something more topological. Oh, but by the way, so I started working on this stuff with Kremnitzer in like 2013, and eventually, like we saw that condensed or pyknotic mathematics sort of achieve similar goals as we get, but we do it in a very different way, and we have advantages and disadvantages to this way of doing it. So, definition. What can you define using this? So F is flat if the connective part it commutes with finite limits. And it's wait. In a second, oh, sorry, I forgot. And it's projective, let's say part 1 to projective. So let's just give it a different name. So P and C bigger than or equal to 0 is projective if the flatness is kind of an obvious thing, but the projective, I guess Laurie defines this originally. Realized that this was the right definition. Commutes with geometric realizations, which are colimits indexed by delta up. This is the mapping space, not spectra. So the underline is an object of C. So it's a stable thing. This is just the top of that space. So colimits indexed by delta. Okay, so that's not, I'm defining what Raxid called the context, but I haven't finished yet. So maybe I'll number the things. Okay, so I have 1 and 2.
So what does it mean, geometric realization on the?
It's a colimit indexed by a colimit, which is indexed by a functor from delta op to C bigger than or equal to 0. It takes colimits to colimit.
Colimit.
Yes.
It's the same thing as colimit with OC colimit. No?
Okay, so I'm gonna now add axioms to what you need for a Raxid context. So 3, oops, let me just call these A and B because I already know. This has nothing to do now with the definition. C. A small full subcategory is specified in the heart. Actually, let me make this D. So D, C is the T structure is right complete. Believe in all the examples, it's also left complete, but no, that's a consequence. And D, you have this small number. It's like that the intersection of the truncations is 0. whichever direction the truncations go when you truncate. Okay. Oh, yeah, so you have a small full subcategory.
The heart is just the intersection of those.
Yeah, so the heart is the, yeah, exactly, the heart is C. Which is closed under finite coproducts, and its objects form a set of compact projector generators. The objects are compact and projected and they're generated. Right. Generators at what? If C bigger than or equal to 0. And last thing is that, let's call it E. This itself, okay, so C 0 is closed under the formation of C heart symmetric powers. I'll say what that means in a second.
Are we defining a context now?
Yeah, this is I'm getting to the end of the definition. So in other words, still, okay. Yeah, so let me just say, so this means that sim n C X is in C0 whenever X is in C0. And that's the end of the definition. But I just want to explain that C heart is also a symmetric monoidal category, and this sim n is just what you think it is. It's the tensor in C heart modulo the action of the symmetric group.
Sorry, when you say modular, we mean fixed points or co-kernels or? No, it's an agreement technically.
Just modulo.
Co-invariant.
Co-invariant.
Co-invariants, okay.
This is
So just note this finishes, so A through E are the definition of a context. Probably taking me way longer than I should have, but the last thing is that C heart is itself symmetric monoidal. Note. And if you have two objects in C heart, you can just consider them objects in C. But the tensor product now is defined not as their tensor product is C, but pi 0 of their tensor product. So you get a symmetric one. Okay, and the thing is that all of this data is actually just determined by C0. Okay, so you can show that if you have C0 satisfying certain properties, let me just go to the next one. So given a given a context, it's actually always true that C bigger than or equal to 0 is P sigma of C0, leaving the product preserving functors from C0 octal spaces, and C is stab of C0. And C heart is, so you can recover everything.
So you could have just started from an abelian category. Right?
Yes, yeah. And no, yeah, you can start with compact projective generators of an abelian category. And I'm gonna give another example now, in a second. So C hard is kind of the one categorical version of C bigger than or equal to 0, where I just go to set instead of space.
So C0 will be something like vector bundles over your geometric thing?
It's yeah, projectives. I'm gonna give an example in a second where it's not sort of where it's something interesting, which is okay. So arXiv was interested in proving HKR theorems in a very non-model categoric theoretic way, and so I'm just gonna I need to go faster, but he defines this monad L-sim in a couple of stages. So maybe I'll go a little bit faster. So he takes you start with sim C heart and you derive it. That's the first thing. So there's two steps. The first one is kind of easy. So derive. And you get L-sim, but not the full one you want. Because I want to extend it to all of C. And extending to all of C is sort of work of Grantner, Matthew, and arXiv. I think I'm gonna, so
Sim, you mean like the direct sum of all the sim ends?
yes,
That's what you want to do?
yes. Yeah, so these also have versions that are kind of n by n, but we need to extend the whole thing. And so anyway, I mean, the deriving part is pretty standard. So it's based on shifted co-limit preserving functors. This is the usual derived functor, which is the fact that this is the same as functors from C0, C bigger than or equal to 0. But now comes the more crazy thing. And this is related to the Goodwillie calculus and excisive things. But in order to extend it to all of C, you have to use their work. And so fun excisively polynomial from C to C, which is where you want to be, is actually equivalent to just forgetting down to, restricting to C bigger than or equal to 0 to C. So you can do it in two steps. First, you start here with your guy, which is L-sim heart. Sorry, which is sim C heart. You have an object here, you derive it, meaning you lift it here, and then you think of it as a functor into C, and then you lift it back through here.
This is given the right cut extension? I mean, the equivalence.
I think so, yeah. Yeah, but the hard work comes into, this is a hard theorem. This
Are your functors continuous over C or there's a threshold? What kind of function to consider?
just functors of infinity. Yeah, so anyway, so I want to get to some like explicit stuff. So L-sim is a monad and algebras over that monad. So you get this category D-alg C. And it does have a map to C algebra C. And if you're over a field of characteristic 0, I think these are the same. Okay, but this one, yeah, this is like kind of a more topological thing. This is a more geometric thing, but in some cases they're the same. But since I'm interested in working over the integers mostly, I better take this one. And usually everything you want to prove about these guys is just more difficult than the same proofs you would do here. So once you know how to prove what you want here, it's pretty clear that, like, you know, how it gives us something there. So now we need to do algebra for these kind of algebras. Okay, so what kind of morphisms are we interested in? And we have like
this stand for.
derived. So derived algebras, commutative algebras, but the derived are also commutative. Yeah, it should be called like DC or something. They're derived commutative. So there's various kinds of morphisms between these, and we have descent theorems for these for the topologies you get. So but now I'm gonna only look at the connective guys for this. Well, flat is like this, you know, the same as I said before. So you would want that.
Anything to do with the divided powers?
Yeah, the d-alg of the unit. Sorry, the LSIM of the unit is the divided powers. So flat is the same as before, it preserves finite limits.
Sorry, isn't the LCM of the unit the finite?
Can't it be both though? I mean, can't it also be divided? I mean, it's the geometrically it's the line, and yeah, I'm not sure. I think you get I think you get like divided powers, but then here they would just become polynomial algebras when you so it's flat if this preserves finite limits, it's an epimorphism.
You don't really understand what's the difference between derived algebra.
So yeah, so derived algebras are algebras for the LSIM operand, but there's another operand called SIM, and commutative algebras can be viewed as algebras for that mono. C-alg is the usual E infinity thing or whatever.
Yeah.
So the difference comes in that this LSIM is different than the SIM thing, which is yeah. The SIM would just be given by the usual formula, the SIM n. So
if you take the example of the right category of a billion groups, then what is the can you?
one of them is so the connective part of D-alg is going to be some simplicial commutative algebras, and the connective part of C-alg is E infinity.
Okay, you just
Okay. So A to B is an epimorphism if B tensor A over B is equivalent to B, and it's gawa if there's a finite group with A is the invariance of G and B tensor A over B is the product of B over G. Okay, so let's finally see what kind of examples we can have that have something to do with analytic geometry. Moving a little bit faster. Okay, so the usual algebraic, so examples. So let's start with C0 to just be the ZNs. Inside all abelian groups, which is going to be C hat. So this gives a arXiv context. This is just going to give you algebraic geometry over Z. The second example is C heart. It's in the abelian category, which is the left heart of end bond Z. This is the one categorical end, where bond Z is just complete normed groups with bounded morphisms. And the left heart is an annoying thing you have to do where you consider pairs of groups up to some equivalence and a monomorphism. Sorry, pairs of objects in end bond. Let me just roughly say that it's this kind of pair where V and W are in the bonds. So these are formal colimits of Banach spaces with bounded morphism. And finally, I need to tell you what C0 is. And the interesting thing here is that C0, even though they're going to be compact objects in the category, they're not finitely generated abelian groups. So C0 is certain collection of Banach modules over Z. And I'm going to use the notation of like a sequence space. So to specify an object of C0, I'm going to just specify a bunch of integers, AS and Z, and a function from S to the reals. Okay, and with the property that the sum over S in S of AS f of S is less than infinity. And the norm on this Banach module is just this thing. So the norm of AS, maybe I should say AS comma F is this sum. So in particular, if you were to base change one of these objects to the complex numbers, and if S were countable, you would get the standard Banach space L1 of C. Let's say if you base change to the reals. Doesn't matter, whichever you want, but there's this projective tensor product which we use. Sorry, if all the if F is just the constant function 1, then this is the space. Okay, so usual objects of functional analysis appear when you base change.
So S need not be countable?
No, S doesn't have to be countable, but for this example, let's just take S to be countable. Because I want a sequence space. In general, if S were uncountable, you would want to place a measure and take L1 of that measure space. But yeah, this is sorry, S can be anything, but for this example, I need it to be countable. Okay, so these are the projective generators, and just to give you an object interesting analytic algebra. I'm just going to give an example of a discrete algebra. So, and you think of this as a disk of radius r. or the functions on the disk of radius r. So fix a Banach ring. So it could be like C or QP. And R of X over R is just polynomials of the informal power series with this sum condition. This is also a Banach ring, and there's an overconvergent version which turns out to be much better behaved, which is X over R dagger. This turns out to be nuclear and have all kinds of nice properties. And if you take a disk of radius r and you shrink down to a disk of radius s by restricting your functions, you get one of these homotopy epimorphisms. So property. Sorry, yeah. So R of X over S dagger completed derived tensor product. R of X over R dagger. But the crucial thing is that the map is not flat. So this is where analytic geometry and algebraic geometry take a huge turn. Because you see, I could tensor with something supported on an annulus here, and I would get 0. Because they're not even touching, right? If I take an annulus here and tensor with the functions there. So, you know, in algebraic geometry, the opens tend to be very big, and the main thing is that this is not flat. With respect to this derived completed tensor product. But, and here's a connection to homotopy theory. If you look at Rognus's article on Galois theory, the same proof goes through to show that these Galois morphisms are dualizable and hence flat. So of the three, I guess, I don't know, maybe it's not on the board anymore, but of the three types of morphisms I mentioned, the Galois ones are flat, but these homotopy epis are in general not flat. And, you know, we were able to prove descent. Since I'm out of time, I won't discuss the Berkovich space, but here's one open question. Maybe somebody in the audience can help me do it. So I would like to classify all of these homotopy epimorphisms. So in the algebraic case, it's pretty easy. A would just have to be Z with some set of primes inverted, possibly infinite. But in this analytic case, I don't know the answer. And I'll just end by saying that there's an interesting version. You look at the Berkovich tree. So we're here at Weizmann, where Berkovich is located. If you look at the Berkovich tree of Z, which is all continuous semi-valuations that are bounded, continuous multiplicative bounded semi-valuations, then there's a certain cover of this in the analytic sense that I'm hoping plays the role of the fracture square in the algebraic sense. So in the algebraic sense, you usually look at Z product over ZP, Q, and their tensor product, and this is a pullback and a push-out diagram. I think it actually, it's, yeah, you can do P or the parentheses P, but if you actually look at these ZPs, they by no means cover the Berkovich space. They just kind of correspond to this line segment. And so there's certain homotopy epimorphisms you can give that are natural candidates for a cover, which I think of as an analytic version of the integral Adele. So thanks very much.